Marketing mix modeling, or MMM, is a statistical analysis technique used to estimate the impact of various marketing tactics on sales and other business outcomes. Robyn employs advanced MMM methodologies to provide insights into the effectiveness of marketing channels. The total effect on sales can be decomposed into base and incremental components. The base sales are the sales that would have occurred without any marketing activities. They represent the underlying sales trend driven by factors such as brand equity, product quality, seasonality, economic conditions, and other non-marketing factors. The incremental sales are the sales generated as a result of specific marketing activities. Incremental sales are directly attributable to marketing efforts and provide insight into the effectiveness of each marketing channel. MMM uses aggregated and historical data, rather than individual user-level data. This makes it inherently more privacy-compliant. As a result, it becomes a more attractive option for marketers who need to adhere to the stricter privacy regulations of a cookieless world. Facebook Robyn is freely available on GitHub, allowing marketers and data scientists to access, modify, and contribute to the codebase. Robyn automates many aspects of the modeling process, from data pre-processing to model selection and validation, making it accessible to users with varying levels of expertise in data science and statistics. The tool provides actionable insights and recommendations for optimizing marketing spend, helping businesses to allocate their budgets more effectively across different channels. 3 key features of Robyn media mix modeling are multi-objective optimization, regularization, and diminishing returns. Let's break down each feature and its significance. The multi-objective optimization uses a normalized root mean square error and decomposition root sum of square distance. This decomp RSSD is Facebook's way of accounting for business logic. If you're spending 90% of your budget on TV and the model says actually Facebook ads drove 90% of your revenue, the model is probably wrong. This measure assumes that your way of currently operating has merit and penalizes models that greatly deviate from business as usual. Regularization is a technique used to prevent overfitting in statistical models. Overfitting occurs when a model becomes too complex and starts to capture noise in the data rather than the underlying trend. This constraint helps to simplify the model and improve its generalizability to new, unseen data. Ad stock models the delayed impact of advertising by acknowledging that the effect of an ad is not confined to the period in which it airs. Instead, it continues to influence consumer behavior for some time after the initial exposure. Over time, the effectiveness of repeated ad exposures can diminish. This concept is known as ad wear-out or saturation. Ad stock helps capture this by incorporating a decay rate, which represents the speed at which the advertising effect diminishes. The related concept of diminishing returns refers to the principle that as investment in a particular marketing channel increases, the incremental return from that investment decreases. Initially, small investments can yield significant returns, but after a certain point, additional investments result in progressively smaller gains. Multicollinearity does not reduce the predictive power or reliability of the model as a whole, at least not within the sample data set. It only affects computations regarding individual predictors. That is, a multiple regression model with correlated predictors can indicate how well the entire bundle of predictors predicts the outcome variable, but it may not give valid results about any individual predictor or about which predictors are redundant with respect to others. In this image, we have 3 planes running through the data, but we only have data points in 2 dimensions represented by the black and white dots. Our model is asked to fit 3 dimensions. Therefore, we have the different colored grids which fit the data equally well. We can think of these grids as alternative coefficients. And because they fit equally well, the regression has a hard time picking one, and this leads to unstable estimates. In marketing data, our channel spends are almost always highly correlated, which means that our channel coefficients are unstable and difficult to pinpoint. We can have equally fitting models with very different coefficients. In this example of ad stock, Channel A, high ad stock retains 70% of the previous week's impact. Even without additional ads, the information sticks. This channel drives long-term purchases effectively. Channel B, mid-level ad stock, retains 50% information, which is a moderate rate. Channel C, low ad stock, retains 10% information. At this level, we lose information quickly. By week 3, practically everything is forgotten. Depending on how ad stock gets set will have a substantial impact on the channel coefficients, with high ad stocks increasing the coefficients and low ad stocks decreasing the attributed impact. Model default is set to 5 trials with 2,000 iterations each. Horizontal axis is measure of fit to the data. Normalized root means square error. Vertical axis is a business logic measure that measures model in relation to historical spend. This is the decomp RSSD, and it's short for decomposition root, sum of squared distance. Evolutionary algorithms with 3 main components are used. First, we have population-based approach. Evolutionary algorithms work by generating a population of potential solutions and iteratively evolving this population based on selection, crossover, and mutation operations. Second, we have selection of parents. Models that perform well on the objectives are selected to contribute to the next generation. And third, we have crossover and mutation. New models, or offspring, are created by combining aspects of parent models and introducing small random changes to explore the search space. The evolutionary algorithm continues to evolve the population of models, which aims to improve the Pareto front over successive generations. Robyn evaluates initial models based on NRMSE and decomp RSSD to balance prediction accuracy and stability of media effect decomposition. Channels with high spend intensity and similar budget ranges are likely to fall into the same clusters as their media effectiveness and may exhibit similar diminishing returns behavior. Robyn accounts for the lagged effects of media on sales or conversions. Channels where the media effect occurs after a delay, i.e., it takes time for the media to drive conversions, are clustered together based on similar lag periods. Channels that exhibit similar saturation dynamics, where their response curves flatten out at similar rates, are also clustered together. The concept of a Pareto front is used to identify a set of models that offer the best trade-offs between the objectives. A model is considered Pareto optimal if no other model can improve one objective without worsening another. Here we can see that the Pareto front is the red line in the lower left of the scatter plot. Note that these different models have similar NRSME but different RSSD. This can be seen visually by the fact that the red line is nearly vertical. Again, lower RSSD more closely aligns the model with current spend distribution. As previously stated, this measure assumes that your way of currently operating has merit and penalizes models that greatly deviate from business as usual. High decom.RSSD indicates a larger discrepancy between the model's predictions and the actual spend distribution results. This does not mean that high RSSD is incorrect, but if the high RSSD were correct, then you are currently doing a poor job of allocating your spending. Someone that is not well versed in MMM might logically ask the question, can AI figure this out for us? The answer is no, because AI is great at optimizing straightforward numerical calculations, but with MMM, we can have multiple models that give highly accurate predictions of our target metric, but give very different attributions. In other words, all the attributions add up to a great prediction, but the individual attributions are very different. We can map our 6 algorithmically selected models and place them on our multi-objective evolutionary performance chart. Any of these models could be our final model, but each might lead to very different conclusions about how to allocate our marketing spend. These are model one-pagers, which give the same set of charts for each model. Here we are comparing the lowest decomposition RSSD with the highest to get an idea of how these vary. Remember, these have very similar NRMSE scores. Each model selected has its own one-pager. In our case, that is 6 models. For contrast, we will examine the highest and the lowest decomposition RSSD. These one-pagers are very helpful information, and we will go through a few of these graphs. First, we will look at the waterfall. This shows how much of your sales are attributed to each channel. The first and highest factor is competitor sales. When our competitor is selling more, then we are also selling more. Our competitor sales, along with the intercept, is not something we can control, so we say this is part of our base. This differs from the things we can control, such as channel spending. These are referred to as incremental. Imagine that we turn off all of our spending. What we would be left with is our base. And anything on top of that would be our incremental. When we go one by one through these, each follows the similar rank orders with some difference in holiday, and we see search and Facebook swapping places. Although the rankings of individual variables in the waterfall are similar, the incremental of the highest RSSD is 50% higher than the lowest RSSD model. When we look at the overall fit of these two models, both are highly accurate with adjusted R-squares of 0.94 for our lowest RSSD and 0.93 for our highest RSSD model. This tells us how well our model describes reality. In these charts, the yellow line is the actuals and the blue line is what our model predicts. This is for the modeling window we gave Robyn. Not only are both models close, when there is separation in the actual and predicted lines, these misses happen in the same places on our timeline. As mentioned before, we are using all of our base and incremental factors to predict our sales, and then we tease out the separate channel impacts based on the coefficients and the response curves. Up until now, we have seen that the model's overall performance and even the waterfall numbers are similar. But when we look at share of spend, effect, and ROES for the individual channels in the modeling window, we see a lot of difference. We have the two bars of dark blue for the share of spend and the light blue for the share of effect or impact. We also have the dot, which represents our ROES. This shows the share of total spend and its corresponding effect across different channels. Differences here indicate variations in how each model attributes spend effectiveness across channels. As you can see in the charts, the low RSSD model has much lower ROES numbers than the high RSSD model. Overall ROES numbers are higher for the highest RSSD model, and this is particularly noticeable for the print and Facebook channels. Again, this is for two main reasons which we have covered before. The first are channel effects of lagging and ad stock. Different models may handle the lagged effect of advertising differently, impacting how the immediate and delayed effects of spend are attributed to conversions. Variations in how ad stock or decay rates are modeled can influence the perceived effectiveness of spend over time, affecting ROES calculations. The second is regularization to handle multicollinearity. Different approaches to regularization, e.g., ridge regression and lasso, can lead to different attributions of spend effectiveness, impacting ROES. There are 3 ad stock options built into Robyn. I have used the default geometric ad stock, which has a fixed decay rate. The other ad stock options use more compute resources and typically take twice as long. In my case, using the included data that would go from 2-hour runtimes to 4-hour runtimes. Response curves are the building blocks for budget optimization and will drive budget shift recommendations from Robyn. You should pay special attention to these and use them as a sanity check in selecting your final model. It is commonly said that coming up with a media mix model is easy, but coming up with the right media mix model is hard. To review, the right model is hard because many alternative models produce excellent fit, but vary greatly in terms of channel weights and business implications. In later videos, we will see how channel weights can be modified through including experimentation results. This calibration is the process of adjusting the model's predictions to align more closely with real-world outcomes. Additionally, there are complexities which are not easily accounted for by the base MMM model. The bottom line is that the aggregated nature of the model can lead to misattribution. As always, thank you for watching, and I welcome your comments.